You are in a dark room, screen light on your hands, watching a tiny red fleck blink out from the edge of time. Its name is Able 2744-QSO1, a faint little red dot hiding behind a faraway cluster of galaxies. If that speck is what James Webb now says it may be, then our story of how the biggest things in space begin is about to bend. Stay close and subscribe for more stories like this, because the next few minutes may change the way you look at every galaxy in the sky. At first, it does not look like much. Not a blazing spiral galaxy, not a bright star field, just a dim ember, stretched by distance, so small it could disappear in a blink. And yet that is part of the shock. The universe often hides its loudest secrets inside quiet shapes. A grain of red light can hold more weight, more force, and more history than whole islands of stars closer to home. What James Webb has seen here is not simply large, it is large too early. That is the part that makes astronomers sit up. Not just the mass, but the timing, like finding a skyscraper in a town where the concrete just dried. So before we talk about numbers, names, and papers, hold on to the picture itself, a tiny red stain in a black ocean. Because this story begins with something that looks almost empty, and ends with a future that suddenly feels much less settled. To see why this matters, we need to step back. Most people, and for a long time most astronomers too, picture the story this way. A galaxy forms first, stars light up, some of those stars die, and only then do black holes grow in the middle. That picture has been so natural for so long that it can feel less like an idea and more like gravity. For most of human history, black holes were not even things you could point at. They were math first, a strange answer hiding inside equations. Then they became hints, then shadows, then engines, and now, with tools like James Webb, they are becoming characters in a much older story. A black hole is simple in one sense. It is a place where matter has been squeezed so hard that gravity, the pull between objects, becomes extreme. Once something crosses the edge, called the event horizon, light itself cannot climb back out. But black holes are also loud in a strange way. They do not glow by themselves. What glows is the gas falling toward them. That gas twists into a hot spinning disk, heats up, brightens, and can outshine whole galaxies for a time. That is why astronomers expected the early universe to play by a slower script. You begin small. You make stars. Some big stars burn fast and collapse. Their leftover black holes merge, feed, and over millions of years become larger. It is a tidy ladder. First sparks, then bonfire. First village, then city. First seed, then tree. And if you are trying to explain the early universe, that ladder has felt safe because it matches how structure usually grows. Space itself also helps hide the truth. The farther you look, the farther back in time you go. A telescope is a machine for seeing old light. James Webb does not show us the universe as it is now. It shows us pieces of it as they were long before Earth had oceans, trees, or bones. That is where the trouble started. Webb began sending back deep images of the early universe, and in those images were little red dots. Not broad, bright galaxies, not simple stars, just compact red objects, scattered through cosmic dawn like embers in ash. Astronomers gave them a plain nickname, little red dots. The name sounds almost friendly. The data did not. These things kept appearing in an era when the universe was only a few 100 million years old, and they did not fit cleanly anywhere. Some researchers thought they might be very massive galaxies. Others suspected hidden black holes. Others still wondered if dust, gas, or strange viewing angles were fooling everyone at once. When one telescope gives you something new, the first rule is humility. Webb had the tools to press harder. Its near-infrared spectrograph, called NIRSpec, can spread light into a spectrum, meaning a color fingerprint. That fingerprint can tell you what gas is there, how fast it moves, and what kind of energy is pushing on it. In November 2025, Roberta Tripodi of the University of Ljubljana and INAF, writing with colleagues in Nature Communications, described one of these objects as CANUCS-LRD-Z8.6. It came from less than 600 million years after the Big Bang. Even then, the standard story still held the stage. The thinking was simple. Yes, these dots looked odd. Yes, they were early, but perhaps they were still just young galaxies doing young galaxy things in messy, hard-to-read conditions. Nothing truly foundational had to break. That idea was easy to live with because the universe often looks chaotic up close. Gas clouds collide, starlight gets absorbed and reddened, gravity bends paths. A distant object can be magnified, duplicated, or smeared by another massive object sitting in front of it. That last trick matters here. Able 2744-QS01 sits behind a huge galaxy cluster called Able 2744, also known as Pandora's cluster. The cluster acts like a lens made of gravity. It bends and magnifies the background light, letting Webb see something that would otherwise be much harder to study. Even so, QS01 is tiny by galaxy standards, about 1,300 light-years across. For comparison, the Milky Way stretches about 100,000 light-years wide. If our galaxy were the width of a continent, QS01 would be a neighborhood. Tiny, distant, dim, and early. Everything about it invited caution. Astronomers have been burned before by overreading faint light, so the safer move was to assume that the old rule still applied. Galaxy first, black hole later. And by the end of this setup, that rule still seems reasonable. Even with Webb's sharper eyes, even with the little red dots multiplying, even with spectra hinting at fierce energy in very small places, the prevailing picture remains standing, calm, and intact. What we have just taken for granted turns out to be a small part of a much larger story. The red dots were not lining up neatly. Their light was too concentrated. Their energy was too fierce. Their timing was too early for comfort. Write the moment your own picture started to wobble in the comments. That small detail helps us build future episodes around the exact second curiosity turns into pursuit. Because the next part does not just add data, it opens the floor beneath the old story and lets us see what has been growing under it. The first cracks came not from a dramatic announcement, but from the slow pressure of repeated measurement. Astronomers expected faint young galaxies. Instead, Webb kept finding compact objects with signs of intense radiation, as if something in their centers was feeding hard and heating everything around it. Tripodi's 2025 team looked at CANUCS-LRD-Z8.6. What they expected was a small, early galaxy with modest activity. What they found was evidence for an actively growing supermassive black hole. It felt like opening a child's backpack and finding a running furnace inside. The galaxy itself was compact and chemically young. It had not made many heavy elements yet. Heavy elements are things like oxygen and iron, forged inside stars and spread by stellar deaths. So astronomers expected a light, immature system. But the black hole did not behave immaturely. According to the Nature Communications result, it was already unusually massive for such an early host. The galaxy seemed young, the central engine did not. The mismatch was like hearing an adult voice come from a locked nursery. That alone was unsettling. Then, the wider population of little red dots began to look less random. In January 2026, Dirac Watson and colleagues at the Niels Bohr Institute's Cosmic Dawn Center argued in Nature that many little red dots are young, supermassive black holes wrapped inside dense, ionized cocoons of gas. What was expected there was even stranger. Some people had assumed the dots might be monster galaxies. Watson's team instead said many may be smaller black holes than feared, often up to about 10 million solar masses, but hidden inside thick gas that changes how their light escapes. That is a key twist. Not every surprise in astronomy means bigger than expected. Sometimes it means differently hidden. Watson described black holes as messy eaters. Most of the gas falling in does not vanish cleanly. A lot of it heats up, shines, and blasts back outward. So the picture shifted again. These little red dots were not just passive lights in the distance. They were active places, violent places, places where matter rushed inward, radiation pushed outward, and the surrounding cocoon tinted the whole scene red. Then came QS01. Earlier studies had already suggested it might be a little more than a cloud of glowing hydrogen and helium circling a black hole of roughly 40 million solar masses. That was provocative, but still indirect. Indirect measurements always leave room for escape. You can estimate a distant black hole from the light around it, but those estimates rely on assumptions. Assumptions built mostly from nearer galaxies. As Francesco De Eugenio of Cambridge later pointed out, nobody knew for sure that the local rules still held in the very distant universe. So the team went after something harder. They used Webb's NIRSpec integral field unit, often shortened to IFU. Think of it as a way of taking a spectrum across different parts of the same object at once. Not just what light is there, but where. Ignace Juodbalis, working with Cosimo Marconcini and others, mapped the motion of hydrogen gas around QS01. What astronomers expected, if mass were spread through many stars, was a more mixed pattern. What they found was clean Keplerian motion, the same basic rule that keeps planets orbiting the Sun. That result mattered because it is a gravity test. If the gas moves as though one compact central thing dominates, then most of the mass is piled into that center, not smeared through a broad field of stars. It was the difference between watching leaves circle a pond and realizing they are spinning around a drain. On 27 May 2026, in a Nature paper and a matching monthly notices paper, the team reported a direct mass measurement, about 50 million times the mass of our Sun, not in a giant mature galaxy, not in a sprawling city of stars, inside a tiny system from just 700 million years after the Big Bang. What was expected was imbalance, yes, but not this much. In nearby galaxies, the central black hole is usually a tiny fraction of the total mass of the host. What was found in QS01 was staggering. The black hole appeared to make up roughly 2/3 of the whole system's mass. Pause there for a second. Imagine a town where the city hall weighs more than almost every home, school, road, and tree around it combined. That is not how towns work. It is not how galaxies were supposed to work either. The center was not just important, the center was nearly the whole story. Then another layer dropped into place. The gas in QS01 appeared to be almost all hydrogen and helium, with very little oxygen or other heavier elements. Its metallicity, meaning its share of heavy elements, was less than about 0.5% of the Sun's. That makes it one of the most pristine environments measured. What was expected in a galaxy feeding such a large black hole was a busier stellar history. More stars, more chemical leftovers, more signs that time had passed and stellar generations had come and gone. Instead, the place looked nearly raw, like a kitchen before the cooking began. That finding hit at the oldest assumption of all. Maybe the black hole did not rise out of a mature galaxy. Maybe the galaxy was still forming around the black hole. Roberto Maiolino of Cambridge called it a paradigm shift, meaning a change not just of detail, but of the frame used to understand the whole subject. Soon after that, theorists had to meet the data halfway. Volker Braun at the University of Texas at Austin, writing with collaborators in the Astrophysical Journal in February 2026, compared little red dot data with models of direct collapse black holes. These are heavy seeds born when vast gas clouds collapse quickly. What was expected in older models was slow growth from light seeds, the leftovers of massive stars. What Brahm's comparison favored was a route that starts heavier, faster, and more violently. It was like thinking a city began with scattered huts, then learning some may have started with a poured foundation overnight. This is where scale begins to swing wildly. The black hole in our own Milky Way is about 4 million solar masses. QS01's measured black hole is around 50 million solar masses, and yet QS01 belongs to a much younger universe, a time when stars and galaxies were supposed to be in early practice, not full performance. The emotional force of that contrast is easy to miss. You can wash dishes, hear traffic outside your window, and still be living in a cosmos where, very early on, some compact objects may have grown faster than whole galaxies around them. Your quiet room does not cancel the violence overhead. But science earns trust by slowing down at exactly this point. Not everyone agrees on every explanation. Some researchers lean toward direct collapse black holes. Some keep room for primordial black holes, objects that might have roots unbelievably early. And some little red dots may not all belong in one basket. That hesitation matters. It tells us the field is alive, not settled. The measurements are getting stronger. But the family tree is still under debate. Astronomers are no longer arguing over whether something odd is there. They are arguing over which origin story best fits the oddness. Even so, the line that has now been crossed is hard to uncross. QS01 was not just another blurry curiosity. Its gas motion was mapped. Its mass was directly estimated. Its chemistry looked primitive. And its black hole sat in the middle like a weight dropped through thin ice. So when people say James Webb may have spotted one of the most massive objects ever found, the honest version is more precise and, in a way, more amazing. Not the most massive thing in the universe overall, but one of the most shockingly overgrown compact objects ever seen this early, when the cosmos should still have been in kindergarten. The reveal is not merely that a black hole exists there. Black holes are common. The reveal is that mass, timing, and environment do not line up with the story many of us learned. The object is not breaking a rule at the edge, it is putting pressure on the rule itself. By now, the old picture has changed shape. Galaxies may not always come first. In some cases, a huge black hole may arrive early enough or form fast enough to become the anchor around which a galaxy later gathers itself. The center may build the house. And here is where this stops being about one black hole and begins being about us. If a tiny red dot can force a rewrite in how we picture cosmic beginnings, then the universe is still full of ideas we are too early to feel certain about. That should humble us, but it should also wake us up. Share this story with one friend who still thinks space news is just pretty pictures. Passing it to that one skeptic matters because this is the kind of discovery that turns a casual glance at the sky into a real habit of paying attention. And once that habit starts, the universe starts feeling much less distant. What changes now is not just a label in a paper. What changes is the order of events we use to imagine the first billion years. If some black holes were born heavy or became dominant before their host galaxies grew up, then the early universe was assembling itself from the inside out in ways we missed. That affects more than black hole origin stories. It touches the birth of galaxies, the spread of heavy elements, the heating of surrounding gas, and even the timing of reionization, the long era when the first powerful sources helped strip electrons from hydrogen across space. A central black hole that turns on early does not sit politely. It eats, it blasts radiation, it drives winds. It can both feed on gas and shove gas away. That means it may shape how many stars a young galaxy can make, and how fast that galaxy can become chemically mature. Think about your own home for a moment. Turn on the oven and the whole kitchen changes. Air moves differently. Smells build. Heat reaches corners you were not thinking about. Now scale that image until the oven is a black hole, and the kitchen is a newborn galaxy only 1,300 light-years wide. That is why follow-up matters so much. The 2025 Canucks team said it was already planning more Webb and ALMA work. ALMA is a radio observatory in Chile that can trace cold gas and dust, the raw material from which stars and structure form. The Cambridge team behind the 27th of May 2026 QSO-1 result also said it is studying similar objects. That is crucial. One weird object can tease. A population can teach. If more little red dots show the same pattern, the case for early oversized black holes grows much harder to dismiss. And this is where date and number precision start to matter. QSO-1 appears at about 700 million years after the Big Bang. Canix-LRD-Z8.6 appears at about 570 million years. QSO-1's black hole mass is about 50 million suns. Its host spans only about 1,300 light-years. The chemistry matters too. Less than 0.5% of the sun's heavy element content. That is not just low, that is nearly primordial by galaxy standards. It suggests a place not yet richly recycled by many generations of stars, which is exactly what makes the black hole's dominance so startling. The observing tools matter with equal precision. NIRSpec's integral field unit gave the QSO-1 team motion across the object, not merely an averaged blur. Program 5015 helped make that possible. The Canucks work came from Webb Program 1208. In this story, the instrument details are not side notes. They are the path from suspicion to measurement. The future questions are now sharper than they were a year ago. How many little red dots are truly black hole-dominated systems? How many formed through direct collapse? How many are wrapped in thick gas cocoons that change the light we see? How many will turn out to be transitional stages that disappear as galaxies grow? There is also a larger practical lesson here. Every time telescopes improve, the universe does not simply look clearer, it becomes stranger in a better resolved way. Webb is not only confirming ideas, it is sorting them, splitting them, and forcing them to compete against better evidence. That means the next discoveries may not look dramatic at first glance. They may look like another spectrum, another red dot, another velocity map, another table in a paper. But if those tables keep showing overmassive black holes in chemically young hosts, the old sequence becomes harder and harder to defend. By late 2026 and beyond, watch the pattern, not just the headline. Do more objects show Keplerian motion around dominant central masses? Do metallicity estimates stay extremely low? Do follow-up ALMA observations find the cold gas reservoirs expected if these systems are still building the galaxies around them? Those are the clues that will tell us whether QSO-1 is rare or representative. And if QSO-1 is representative, the emotional shift is profound. The early universe may have been less like a field of seedlings and more like a landscape where some towers shot up through the fog almost at once. Not everywhere, not all the time, but enough to change the map. Something else changes too. The story of cosmic history becomes easier to feel in daily life, because the next time you see a tiny red notification light or a distant airplane crossing a dark window, you may remember that far out in space, small bright points can hide systems that outweigh our expectations by millions of suns. More measurements are coming. More little red dots will be sorted. Some explanations will hold, some will fail. That is the healthy part. A living science does not protect old stories. It tests them until only the strongest parts remain. What comes next will arrive quietly. Another observing run, another process spectrum, another paper posted before dawn. And somewhere inside that new data, someone is going to find one more point of light that refuses to behave like a minor character. The next horizon is not just bigger telescopes. It is better patience, better comparisons, better courage about being wrong. Because once you accept that a tiny early object can carry a black hole far too dominant for the old script, you start looking differently at everything nearby. So save this video and come back when the next Webb follow-up lands. That small private habit will help you track the story as it changes, instead of meeting it later as a finished headline with all the surprise already drained away. The universe rewards people who return. Maybe that is the image to keep. Not a giant explosion, not a swirling movie shot, just one little red dot, triply lensed behind Pandora's cluster, holding a black hole of about 50 million solar masses inside a system barely 1,300 light-years wide. A tiny mark, a huge weight. Light that traveled more than 13 billion years to tell us that some of the universe's deepest structures may have begun in the wrong order, or in a better order than we imagined. And I think tomorrow, and the year after that, we will hear this story again in new forms. Another dot, another mass estimate, another crack in an old assumption. Not because the universe is trying to confuse us, but because it is still generous enough to surprise us. So look up with a little more patience. Look at the quiet things longer. The future of astronomy may not arrive as a bright, obvious monster. It may arrive as a faint red speck, barely visible at first, and still heavy enough to move the whole story.